H arrow L. Does this look like a push? It's like a, I should go like this, like a push, okay? This actually is called the PGF, PGF. There's all sorts of little, and that's one of them. That stands for pressure gradient push or force, pressure gradient force, okay? So the pressure gradient force is what's moving that air from high to low pressure, PGF. Okay, so I got a kick out of kind of looking up the Coriolis Force again. This Coriolis Force, if you look it up on the internet, there's all sorts of things. This is actually why you think that your toilets in the northern hemisphere, the water goes down them differently than if you're in the southern hemisphere. But it doesn't. So I posted a few things on my Twitter feed to try to show you it does not. Because sometimes students will argue with me about that.
We had that argument. I'm pretty sure it was my fault.
Yeah. I looked it up several cases, and it's a misconception out there. But what the Coriolis Force is, though, is basically anything. It's kind of fun. Because here's our globe. Of course, the Earth is rotating. You know, it spins once every 24 hours. Okay. Basically, and I like that picture of the rocket that movie did. Basically, once that rocket leaves the ground, okay, the Earth spins underneath it. So if we're to fall back down, straight down, just go up and fall back straight down, and fall in a different location. Coriolis Force. Coriolis effect, basically. It's not a force. Sometimes it's called the effect. It makes more sense to me. Okay, so once you leave the Earth spins underneath you. Okay, that's it. So it's almost like an apparent sort of what we call deflection. It looks like you're changing your trajectory, but it's really the Earth spinning underneath you. Okay? But the thing is that the larger the scale of the motion, okay, the farther something's going to go once it's left the Earth, the faster it's going to go, or kind of the larger scale, the faster. That's when you're going to see basically an apparent, what we call deflection, an apparent change in its motion, but it's not changing its motion. The Earth is spinning underneath it that's left the Earth. So you're going to see that actually this kind of spin is different depending upon which hemisphere you're in. And I'm going to try to show you what I mean by, in the northern hemisphere, deflection is to the right, and I get my left and rights mixed up, so I have to concentrate. So this is my right. So deflection is to the right, okay, in the northern hemisphere. In the southern hemisphere, it's to the left. Okay, so that's how that goes. Basically, you have to stand up like you're hovering over the Earth and go like that. And that's what it's going to be. Okay, that's the apparent deflection in the northern hemisphere to the right. So let's take a look at a jet. In this first scenario, basically, the jet is supposed to fly from the North Pole to the equator. This first example is the Earth is not spinning, which is a very scary thought. Okay, and they picked one line of longitude, 90 degrees longitude. Looks like it must be right around here-ish. Okay, so follow a line of longitude down. Okay, Earth not spinning. Basically, you hover over, like all matches up. But that's not the case. What's really happening is that as you and your jet leave the Earth's surface, the Earth spins underneath you. Okay? And as the Earth spins underneath you, basically, when you go to land, you're going to land over here. In this example, they they set off at 90 degrees longitude. They went straight, but they landed at 105 degrees longitude. 15 degrees longitude west. Why? Because the Earth spun, the Earth was rotating underneath it. So even though it really went straight like that dotted line, its apparent path was the solid line. Its apparent path was the solid line. Now let's look at what deflection was. So you have to go up there at the North Pole, go towards the equator, and can you see where it looks like that? That is the right deflection. Deflection to the right. The apparent deflection. That's the Coriolis Force. Large scale, right? Going from the North Pole to the equator. Okay. But chunks of air that actually are not on the Earth. They're hovering over the Earth is spinning under that chunk of air. So it will also seem to have an apparent deflection too. All right. So let's look at not going like a line of longitude, but let's look at a couple scenarios where there is a chunk of air, or could have been a jet, but it is actually going to try to follow a line of latitude. So in this case, it's at 60 degrees latitude, it's hovering though, and the Earth is spinning, okay? So as the Earth spins, okay, it looks like it's different. It's deflecting to the right again. So that's 60 degrees latitude. There's 40 degrees latitude, 20 degrees latitude, and there is the equator. So one of the things you might notice that at the equator, basically it hovers, the Earth spins, okay, but there's no apparent deflection. There's a little bit of deflection, apparent deflection at 20 degrees latitude, more at 40, and the most at 60 on this drawing. So that's another rule. I have a slide that says what are the rules of the Coriolis effect or the Coriolis force, that kind of apparent deflection as the Earth spins. One of the rules is the higher you go up in latitude, the greater the effect. When we talk about hurricanes, otherwise generically called tropical cyclones, we're going to see that even though here at the equator it's nice and toasty, you think hurricanes galore. But one of the things hurricanes need is a little bit of twist. No twist, no Coriolis force, okay? Hurricanes can't form here.
Maybe that rotation is why planes can fly through them.
No, I don't think so. But they do need a certain amount of rotation.
I'm trying to figure it out. It's still bugging me.
I can tell. So here's my whole list of things for the Coriolis force. It's an apparent deflection, I think, just because the Earth is moving underneath the object that has left the Earth. And, whether it's a jet plane, whether it's a chunk of air. Air, do you buy this? Air is like a fluid, and oceans are like a fluid, right? So actually oceans can have this sort of Coriolis force too. This will make more sense here in a minute, but we're going to see that actually the Coriolis force is at a perpendicular or right angle to the motion of the jet or whatever it is, the chunk of air. We said that it's strongest near the poles and basically zero at the equator. Okay, these are all important things. It's to the right in the northern hemisphere, to the left in the southern hemisphere. And I already said you have to be going pretty darn fast, okay, and be going a far piece in order for the Coriolis force to be observed. Notice that it only changes the direction of motion, not the speed. The thing that affects the speed is the PGF, the pressure gradient force. That affects the speed. All right. So the Coriolis force will basically we're going to see large chunks of air go to the right in the northern hemisphere. So the other thing that changes direction once your chunk of air is moving because of your pressure gradient force, this is actually called wind, right, is friction. And the good thing about this topic is it's something that everybody's familiar with. So this is wind. Everybody's familiar with friction. The smooth surfaces basically don't have friction. The rougher the surface, the more the friction you have. And there's something called the coefficient of friction that would go along with that. So here's one for you. Basically, we think of kind of the air moving kind of in horizontal layers like this, where basically the layer of air that's close to the Earth, that's who's going to get the friction, okay? The thing about the second layer up here, it's actually got friction from the layer underneath it, okay? This third layer, it's got friction from the one underneath it, okay? But the deal is this has less friction than this does, okay? So the most friction is here, less and less friction. So honestly, and I usually have to chase this down every semester to remind myself how it works, but as you go up in elevation, the winds get stronger and stronger and stronger and stronger, okay? At some point, though, the winds start to get less. So going up in elevation, your winds increase in speed. So you see the word A-L-O-F-T, one of my favorite words, aloft. Okay. Sometimes we're also concerned about what's happening here. Well, we should be. But actually, it's kind of a big picture sort of thing. What's happening aloft is a player. All right, speaking of what's happening aloft, so this whole upper atmosphere, think of the word aloft. Okay, so winds in the upper atmosphere may be just very totally different than kind of our little skirmishes here. It's kind of like Kane said about the oceans don't have trees and stuff like that to kind of, that's a friction, right? They don't have that friction to slow them down. Okay, at upper elevations, they just go. Okay. So I want to start to set you up for kind of looking at, or maybe we already have been, at kind of global winds. So like this slide says, picture yourself, basically consider what's happening at the poles and what's happening at the equator. Now, one of the things you guys know, it's hot at the equator, right? It's cold at the poles. And one of the things I talked about in this chapter 6 just tonight was with heat, you think of low pressures, right? Okay. And with cold, you think of high pressures. Here's where I need to change that a little bit. Let's see if I wonder if it's on my next slide. I think I'm going to go ahead and okay. I'm going to try this. Okay, so 0, if I put a 0 degrees, what is that?
0 degrees.
It's the equator, right? Very good. Okay, and up here, I'll go ahead and kind of flatten it out. This is going to be my 90 degrees. Okay, so that's my poles. Okay, so this of course is cold. This is hot. All right. So here's the deal. When I say this is hot, I'm going to go ahead and say hot surface, cold surface. I'll tell you why that is. Okay, if it's hot at the surface, then basically, how do I make this three-dimensional? Oh my goodness, I can't.
Go back over to the globe.
Well, I guess. Like over here, so if it's hot here, okay, we have a low pressure here, but basically, can you see where if it's hot up here, actually, I'm going to have kind of a high pressure compared to over here. Let's look at over here what happens. It's so cold that all those cute little molecules are basically so dense down there. When you go aloft, it's a low pressure. It's a low pressure up here. That was going to be my point. I don't know if you can envision this, but it's a low pressure up here and it's kind of a high pressure up here. That's why this slide says basically at upper elevations, we have basically a high and a low. So wind wants to go like this. On the next slide, you're going to basically see wind wants to go like this. And the Coriolis force is going to deflect it, and it's going to deflect it to the right. It's going to go like that at upper elevations.
Easterlies, right?
Sort of. Actually, we're talking aloft, and the easterlies are kind of lower level. Aloft, all of the wind goes this way, okay? And actually, the polar easterlies go that way.
Oh, well, words.
Yeah.
Well, wait.
Yeah, you have polar easterlies, the mid-latitude westerlies, and the trade winds are the easterlies too. But at upper elevations, I don't know if you saw me sneak, so at surface winds here in this unit, we're going to talk about these go east, these go west, these go east. You're like, dude, these up here, they all go, what am I saying?
They all go east.
Yeah. Yeah. Something right. They all go east. Let's see if I said that right. Okay, so that's what you're going to see on the next figure. So I want you to think aloft. Okay, And the reason it says basically we're going to start from the equator and go to the poles is because at upper elevations we have a high here and a low here. Santa Claus is a low. All right. So on the next slide, I want to introduce you to something called geostrophic wind. Geostrophic wind. So the geostrophic wind is basically wind that has gotten in the groove. Okay, and by the groove, I mean it is like cruising between isobar lines. So what I tried to describe was basically a high pressure here, and on the next slide you're going to see isobars. High, lower, 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 lower. Geostrophic wind is in the groove. Basically it is kind of whipped around because the Coriolis Force, and it's flying between those isobars. That's it. That's geostrophic wind. Okay, so here we go. Upper elevation, you can kind of see, down here we have, towards the equator, we have hot. Of course, this would make a low pressure down here, but a high pressure up there relative to towards the poles. Okay, so this is at upper elevations. The red line over here from left to right, this is what we talked about. Basically, that red line is showing wind going from a high to a low pressure. The deflection is to the right, okay? Notice that your pressure gradient force, that red line, it's always going to point from, in this case, aloft from the equator to the poles, equator to the poles. Deflection's always going to be to your right until it basically is right between the isobars. That last purple line there, okay, that last purple wind, can you see it's in the groove? Geostrophic wind. That's a wonderful thing. So that happens at upper elevations, yes, and that felt weird to me because it's been a year since I taught that. But yeah, upper elevations, it's an easterly wind. No, that's a westerly wind. Dude.
Words.
It's coming from a west. Yeah. It's a westerly wind. Okay, the way they do the LY for the direction it's coming from. Yeah. And so.
Yeah, which means what I said was still right.
Okay, good. I got
You said
it.
it wrong.
I think I did. Okay, good. I'm not.
I said
I'm with you.
I said the wind was going to the east,
Okay,
which means
it's
it's
westerly. Yes, very
Yeah.
good. I said it wrong. Okay. All right. So those upper westerly winds. Final answer. Those upper westerly
Are we
winds.
gonna talk about the polar vortex at all?
We'll get there. Yeah.
Okay, cool. 'Cause that always-
Not officially, but unofficially. I'll show you where that. When we talk about the jet stream,
Okay.
that will. When we talk about.
Which probably isn't that far away from
Right.
winds.
Right, those will be the global winds, not the local winds. Okay, so I need to explain what these lines are. You're like, dude, another line? So we had isotherms, we had isobars, now these are isoheights. So basically, they are the height you need to get to 500 millibars pressure. So to kind of remind you to put that in perspective, basically if we're walking around here, we're at 1,013 millibars in general. Today's pressure is kind of high, but 1,013 millibars. So 500 millibars, you'd have to go up in elevation. You can use them just kind of like isobars, though, even though they're isoheights. So we have the company, how fast the wind is moving. Again, you can kind of look for tight pressure gradients, tight changes. That means that you're going to have stronger wind. Loose gradients means that you're going to have weaker wind. You can almost kind of see that with the more flags over here, less flags over here. Another thing I want to introduce you to, you probably already see the L's. The pairs of L's is up there and the pairs of H's down here. I want to introduce you to something called ridges and troughs. Okay, so this is at upper elevation, okay? 500 millibars better be at upper elevation. So these are isoheights. So you might have heard weather people talk about ridges and troughs before, but they look like a kink, kind of like a kink, goes up and it kind of kink comes down. Okay, we're going to talk about something, I love this term, called Rossby waves. And Rossby waves are just kind of like the little kinks in kind of the flow of stuff. And those kinks are important players in giving us our weather. Okay? So ridges are associated with high pressures, and troughs are associated with low pressures. All right. So geostrophic wind was basically, we said, that's wind moving between those isobars, geostrophic wind. Geostrophic flow in general is kind of the motion of that geostrophic wind. There's this, and sometimes I'll like think about this Bayes-Ballott's law, and I don't emphasize it much in this class. I don't even know it's in this edition of your textbook. But it's supposed to be kind of a cool sort of thing, the way deflection is to the right in the northern hemisphere. If you put the wind at your back and you hold out your left hand, that low pressure will be where your hand is pointing, to your left. And high pressure will be on your right. So there's too many GRs. There's like too many R's of reflection, refraction. There's geostrophic. I guess that's not GR. There's geostrophic, too many G's, and gradient winds. But they are related. Gradient wind is basically kind of that geostrophic wind that's moving in kind of curved isobars. You're like, how could I get curved isobars? I will remind you of the bullseyes that we looked at a few slides ago, where we had a central high pressure or central low pressure with kind of the circles around it. Those circles, those are isobars. Okay, so this curvy wind is actually going to go around those. Okay. So here we go. This is all good. This actually, on our weather map, is this middle, see the bullseye? I'm going to kind of reveal parts of it. But you see the low in the middle of the bullseye. Those are actually isobars to kind of show you how that works. Notice that they should make sense. So if that's a central low, then those isobars should be getting bigger, and they are. They go from 1004 to 1008 to 1012. Okay? So we have a central low with increasing pressure. So let's talk about this whole deflection thing. We said that if that's low, then this must be high, relatively speaking. So then basically air is going to want to move from the high to the low, right? So the red is your pressure gradient force. The blue is your wind. The black there is your Coriolis force. So here we go, stepwise, that chunk of air going from the outside in. Here it goes. Can you see it's the pressure gradient force is always pointed there, but our deflection is to the right. Okay. At some point, it's going to become that, it's going to fit in the groove. It's that gradient wind. It's wavy geostrophic wind, basically. Okay? It's in the groove. You think it's going to stay in the groove? It is. Okay? Basically, once it kind of came in, it's going to circle. And actually, now I'm going to kind of point to the ground here. Those, when we look at a weather map and we see the L, we look at a weather map, we see the H, we look at a weather map, we see the blue line for the cold front, the red line for the warm front. We're talking about stuff at the surface, basically, okay? 8 feet above or so. So basically what we have here is a, let me put this whole thing up, because this is kind of neat, I think. These are all things about low pressures. Okay? These are all things about low pressures. First off, they're called cyclones. I don't know if this is first off, but these L's are called cyclones. The weather chunk is called a cyclone. You know, don't be scared. Don't think it's a tornado. It's just a cyclone. Okay? Just a cyclone. Right? But actually, central low pressures can bring us stormy weather, and we're going to talk about that too. The other thing is, can you see where movement is going to be counterclockwise? Counterclockwise. And actually, that's why they call it a cyclone, because if we were to look down at, I'll switch gears and look at the Earth, actually the Earth is spinning counterclockwise. Around a low is counterclockwise. That's why it's a cyclone instead of an anticyclone, which is a high. Okay, so counterclockwise. They're associated with troughs that we saw a minute ago. Air will be converging in the center. Does that make sense? You know, we've talked about convergence before.
It all wants to be at the lowest point,
Yeah.
so it's going to Oh,
It will generally be converging, and we have to kind of fix that in a minute, because it's like, dude, if it's converging there, then basically it's going to kind of pile up there, and that could actually kind of convert it from a low to a high, where it's all, so we'll have to fix that in a minute. But this is a cyclone. These are these surface low pressures. So let's switch gears and look at an anticyclone. Anticyclone is the opposite, so it has a high. Let's make sure it's a high. So if it's a high, that means as we step out from the high, we should be getting lower numbers. So we have 1,024 millibars, 1,020 millibars, 1,016 millibars, so that's all cool. So we said that actually to go from a high to a low, it's going to be fighting its way out, right? Okay, so here we go. Here's that chunk of air wanting to basically get out of the center. Well, it's going to be deflected to the right. So you see the pressure gradient force in red, the wind movement in blue, the Coriolis Force in black there. Okay, and the Coriolis Force will go ahead and deflect it until it turns into a gradient wind. A wavy geostrophic wind, gradient wind. Okay, it's in the groove now. It's going to stay in the groove. But notice which direction it's moving. Okay, clockwise. This is an anticyclone. It's in the northern hemisphere. If you look down at the North Pole, usually the Earth is spinning counterclockwise. So around highs, it's always going to be clockwise. And here's the other stuff. Okay, so the movement is clockwise. Actually, I don't know if you remember, but one of the things I wanted to talk about earlier was these large ocean basins. Here, let's pick on North America. I said if we look at the Atlantic and if we look at the Pacific and if we look at the Atlantic, we basically have these kind of ocean gyres that are going clockwise, okay? And actually we have a big old H there and a big old H there, just hovering. That's what makes these clockwise. Okay, so it's a player in all of it. So air will be diverging from the center, but again, if air is diverging, you're like, dude, eventually my high pressure is going to be sparse low pressure. So we kind of have to address that too. Okay. So the force of friction, how does it affect movement? Not so surprising. Basically, if your movement is this way, the force of friction is kind of the opposite direction. Force of friction, that's why we build snow fences out in the middle of nowhere, because we're like, we want the snow to stop flying to a particular location. Quite appropriate. Okay, so this is what I wanted to try to get to today. So you have to pay attention to what your figures are talking about. Now, figures are not talking about aloft here. Figures are talking about surface. Okay, so we have a surface high pressure, and can you see the clockwise, right? And we have a surface low pressure. See the counterclockwise. That's always kind of fun to start looking for those surface features. And what this kind of complains about is if, it's what I said a minute ago, your high pressure, basically, it's cool, it starts out as a high, but basically, just because it is a high, you have air moving out of the region, so it's going to convert to a low. We are going to talk about a mechanism that basically feeds that high. Similarly, your low, you're going to have convergence there, and it's going to convert to a high. So here we go. In order to fix that, basically, we go ahead and look at conditions up here. Remember I said what's happening up here is a big player for what's happening down here. So in order for your anticyclone, now, if you're like me, you have to concentrate because I'm not a good memorizer. Anticyclones are highs. Obviously, I got my easterly and westerly mixed up. So anticyclones are high. In order for them to stay high, basically, they need to be fed. And they are basically fed by a column of air that is basically converging aloft, going down, and feeding them so they can maintain a high. That's it. converging air aloft. Subsiding means moving down. Okay, so if we look at, I'm going to go ahead and put an L. I'm going to put an H on the first one and an L on the bottom one, just to make sure we're all on the same page here. This is an H and this is an L. It will really help you in this class if you kind of get these under your belt, because they'll definitely be on your exam. We'll kind of keep talking about anticyclones and cyclones. So for that low, to maintain a low, instead of stuff building up, basically you got to get rid of it. So the way you get rid of it is by air rising, okay, aloft, and diverging aloft. Okay, I'll kind of try to show you what that looks like on a 3D picture, which, yeah, I could not do a 3D picture. Here's your 3D picture. I like it. Might have bought the textbook just based upon this picture. Okay, so basically you see your high. We said in order to maintain that high, basically it needs to be fed. Okay, so that's why you have air descending. And how can air descend? Well, if it converges aloft, it can descend. That's it. 3 dimensions. So you're like, this low pressure, it's got to be careful because air's converging there and it's going to turn into a high. So how do you keep it low? Well, you get air out of the way. How do you get air out of the way? You make it go up. So that converging air ascends. And how can it ascend? Well, if you're creating kind of a vacuum aloft, diverging air aloft. So I just think this is a good figure.
And that's how you get tornadoes there at the bottom.
Could be. It looks like it, doesn't it? Okay. Well, that's how far I wanted to get. So that is very good. Bumping up right against 620 or 820, however you want to say it. So this chapter won't be due, but we'll definitely get through this chapter and maybe even the next chapter next week. Okay?